Good morning to everyone. I'm Dr. Sumi MS. The name of the course is Electromagnetic Fields and today's lecture topic is Maxwell Ampere Law. On completion, the students will be able to understand Maxwell Ampere Law and solve problems on displacement current. Maxwell Ampere Law. The progress in the theory of displacement current can be traced back to a famous physicist named James Clerk Maxwell. Maxwell is well known for Maxwell's equations. The combination of four equations demonstrated by Maxwell demonstrates the fundamentals of electricity and magnetism. For displacement current, we will be focusing on one of these four equations, which is known as the Maxwell Ampere Law. Before Maxwell, Andre Marie Ampere had developed the famous equation known as the Ampere's law. This law relates the magnetic field surrounding a closed loop to the conduction current I traveling through that loop multiplied by a constant known as the permeability of free space. So the equation can be given as integral over B ds is equal to mu naught I, where B is the magnetic field and mu naught is the permeability of free space and I is the conduction current in the loop. Whenever there is a continuous conduction current, Ampere's law holds true. But there are also certain cases when problem arises in the law as it is written. For example, in the case of a circuit with a capacitor in it, when the capacitor is charging and discharging, current flows through the wires creating a magnetic field, but between the plates of the capacitor there is no presence of current flow. According to Ampere's law, there can be no magnetic field created by the current here, but we know that there is a magnetic field existing in this case. Maxwell realized this discrepancy in Ampere's law and modified it in order to resolve the issue. The modified law is given as integral B ds is equal to mu naught multiplied with I plus epsilon naught d pi E by dt. This is the final form of the equation which is known as Maxwell Ampere law. Part that Maxwell added to it is known as the displacement current ID, and that can be given as ID is equal to epsilon naught d pi E by dt. The above equation consists of two terms multiplied together. So Maxwell has added the displacement current along with the Ampere's law. So in the above equation, the first is known as the permittivity of free space epsilon naught, and the second is the derivative with respect to time and electric flux. Electric flux is defined as the rate of flow of an electric field through a given area. By taking its derivative with respect to time, we can consider the change in the rate of flow over time. Need for displacement current in Ampere's law. Ampere's circular law for conduction of current during charging of a capacitor was found to be inconsistent. Therefore, Maxwell modified this law by introducing the concept of displacement current into it. Displacement current plays a central role in the propagation of electromagnetic radiation such as light and radio waves through empty space. It is required to make the conduction current lead in the circuit. Conduction current in wires can be made to lead the voltage by means of displacement current inside the capacitor, and hence it has vast uses in induction motors, industrial appliances, and also in day-to-day life. Solved examples based on displacement current. Example 1. Instantaneous displacement current of 2 amperes is set up in the space between two parallel plates of a 1 microfarad capacitor. Find the rate of change in potential difference across the capacitor. So here in the capacitor, we have the displacement current as given as 2 amperes and the capacitance of the capacitor as 1 microfarad. And the potential difference is given as Q by C, and its rate of change is given as I by C, where I is the current, displacement current, and C is the capacitance value. Substituting both, we get the rate of change in potential difference across the capacitor as 2 into 10 raised to 6 volts per second. Example 2. A parallel plate capacitor with plate area A and separation between the plates as D is charged by a constant current I. Consider a plane surface of area A by 4 parallel to the plates and drawn between the plates. What is the displacement current through this area? Electric field between the plates of the capacitor is given as E is equal to Q by A epsilon naught, and substituting Q as IT we get IT by A epsilon naught. Electric flux through the area A by 4 is equal to pi into E, that is A by 4 into E, which is equal to IT by 4 epsilon naught. Then adding the displacement current is equal to epsilon naught d pi E by dt, and substituting the above value of flux into it, we get the value of displacement current in that area A by 4 as I by 4. Example 3. A coil that has 700 turns develops an average induced voltage of 50 volts. What must be the change in the magnetic flux that occur to produce such a voltage if the time interval for this change is 0.7 seconds? Here given the number of turn as 700 and the induced voltage as 50 volts and the time interval as 0.7 seconds. Using Faraday's law, we shall write the induced voltage is related to N d pi by dt, and substituting the given values, we can obtain the change in flux d pi as E into dt by N, which is equal to 0.05 Weber. Quiz questions on Maxwell Ampere law. Give a note on Maxwell Ampere law. Instantaneous displacement current of 2 ampere is set up in the space between two parallel plates of a 1 microfarad capacitor. Find the rate of change in potential difference across the capacitor. Thank you.